Hi everyone, and welcome to lesson 2 on Coulomb's law. So we have two related learning objectives here. For this lesson, we're going to learn how to use Coulomb's law to analyze the forces that occur between charged particles, between charges, and apply Newtonian mechanics to charged particles. So for Coulomb's law, and for when we're dealing with charges in general, we're going to sort of apply the particle model to them, sort of like how we did in Physics 151, where instead of worrying about a whole object, right, and where's the center, where are we measuring to and from, we just treated it as if it were a dot or a particle. Okay, that way we didn't have to worry. It was just one point in space. And so for charges or charged particles, okay, so not everything has to be an electron or a proton. We can have particles that are charged. There could be dust particles, there could be they could be electrons, they can be glass beads, it could be all kinds of things, little things that could be charged, okay? And so if that's the case, if we're just dealing with a little ion or something like that, something tiny, then we can call them charged particles or point charges, and we can apply the particle method to them. Okay, and so so when we talk about charged particles, we can think of them as points or particles, and this model works as long as the separation between them, between these particles, points, is significantly greater than their diameters or their sizes, right? So if they're really close, right next to each other, and separated by fractions of a nanometer or something, then we might actually have to worry about the diameter of a particular particle or charge or atom or electron or something. Okay. So remember that we learned that like charges will repel one another, and so there's a certain amount of force of repulsion when they come near each other, and this force, the way we can determine the magnitude of this force is by what we call Coulomb's law, and so Coulomb's law, I have it stated here. And there's, since we're dealing with two things, the force between two things, we have to always consider Newton's third law of motion, that there's an equal magnitude of forces in opposite directions, right? So the force that if you dropped your phone or something, the Earth exerts an equal amount of force on the phone as the amount of force that the phone does on the Earth. And the only reason that the phone actually moves toward the Earth is because it has less mass, therefore more acceleration. So it's going to move, whereas the Earth is so massive that tiny bit of force is not going to cause it to have a ton of acceleration, a ton of motion. Okay, so two forces, two charges. So here we have two positive charges, Q1 and Q2, and so they're going to exert an equal force on each other. So we would say that charge 1 will exert a force of F1 on charge 2. So charge 1 exerts a force on charge 2, and charge 2 will also exert a force on charge 1. And so we can see those with the arrows here. They're going to point in opposite directions. And so they're going to be equal in magnitude, just opposite in direction. And so this is Coulomb's law here. And essentially we're going to learn about several constants that have been discovered to understand electricity and magnetism. And so K is going to be one of them. And K is the electrostatic constant. And it's 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. So I will usually, when I do problems, I'm just going to round that to 9. 9 times 10 to the 9th, just while I'm doing example problems for you. And since there's so many units going on here, really it is best practice. Remember to always include your units as you're working out problems. That way you can see if you made a mistake anywhere. But you'll see just by nature of trying to do this on the iPad and showing you everything, sometimes there's not a lot of room. So sometimes it will leave the units out. So that's bad practice, but that's something you'll notice I might do. So we have this electrostatic constant, okay, and then the force is dependent on that, and it's also dependent on the magnitude of the charges. Okay, so you notice the absolute value bars around the charges. Okay, and this is because remember a charge can be positive or negative. Okay, and so the positive or negative is irrelevant to the magnitude of the charge. So we don't magnitude of the force between them. And then it's divided by the distance between them squared. So R would be, this would be R, okay? And it would, so if there are tiny charges and the distance between them is big, then it's just the distance between them, okay? If they're very close, then we'd actually have to, the distance R would be from center of one charge to the center of the other, okay? So we'll look out for situations where we might have to consider also the radius of the charges as well as the distance between them. Okay, and one thing I want to point out here is that we briefly in Physics 151 we learned about what we called Newton's universal law of gravity. We didn't do a whole lot with it, but we did use it. If you took the course with me, then we did use it to try to predict what the acceleration due to gravity was. And then we saw that it wasn't quite right. It was like 9.83, I think. And then once we learned about rotation, we started learning that, well, the reason that calculation was off was because we didn't consider the rotation of the Earth. So, but I want to point it out here because the force, if you recall, was this capital G, this gravitational constant, times the magnitude of the two masses over the distance between them squared. Very similar, don't they? Okay, and so when we wanted to find the force between that say the Earth and Moon exert on one another, we calculated the gravitational constant. We took the mass of the Earth and the mass of the Moon, and we divided by the distance between them squared. And so since the diameter or radius of the Earth and Moon are very large, we did have to do that where we did not just the distance between them, but also had to add their diameters as well. And we get a force from that. Okay, so I just want to point out how that's a very interesting thing that we see in nature here. That it works essentially the same way with electric charges, the forces between charges. Okay, so that's how. So we have a repulsion between like charges, and if we have opposite charges, though, remember that they attract one another, and this is exactly the same scenario here, where the force is going to be the same. The direction is just going to be towards each other as opposed to away from each other for repulsion. Okay, but we still have this action, like reaction pair, right? The same force exerting forces on one another. It's not one thing's exerting force and nothing is happening with the other. They're both exerting a force. Okay, so if we want to think about this concept, then think about this question: the charge of object 2. So we'll call this object 2 here, this large object that has two positive charges in it. And we said that the charge is twice of object 2 is twice that of object 1. So two charges in object 2, one charge in object 1. And they're near each other, so they're like charges. They'll repel one another. Okay, so what does the vector of the force of object 2 on 1 look like? Well, we're given here what the vector of the force of object 1 on 2 looks like, right? They're going to repel, so they're going to go in opposite directions. And so object 2 is going to move this way, right? Because, so F of 2 on 1 is the force that object 1 exerts on object 2. And so what is this force vector going to look like, right? It's going to, right? Hopefully you know that it's going to point in the opposite direction, okay? But remember the vector is represent the vector. We represent a vector pictorially with an arrow, and the length of the arrow has to do with the magnitude. So what's the length of the arrow going to look like? Right, we know it's going to go this way. Is it going to be twice as long as this arrow, since object 2 is twice as much charge? Okay, if you want to pause and think about that, that'd be a good idea. Okay, well, it's actually going to be the same. Okay. So if I could perfectly draw that to be the same length, this arrow is the same length as this arrow. Yeah, that's what it is, right? It has nothing to do with the size of one object versus the other, or the amount of charge of one object versus the other. They're both going to exert equal forces, right, in opposite directions. So this would be F of 2 on 1. Okay, so try to keep that in mind. Try not to mix that up. Remember Newton's third law here. Okay, so I mentioned in the previous lesson we looked at the electroscope and also the pith ball. And with the pith ball, remember, it was very light. It was suspended by a string, and it was able to move around and be attracted to a plastic rod that was charged. But recall I mentioned that with the electroscope, when I brought the charged rod near the electroscope, it would not be, it's attracted to it, but it's not going to jump up and move toward the rod, right? Because it's just far too heavy. Well, here's a situation where it might actually be possible for the object to move up, to jump up, to levitate, to oppose gravity, okay? So we have, let's say, a small plastic sphere charged. All right, so a small plastic sphere here, all right? Maybe it's charged and I'm holding it with a rod or something. Yeah, you can try to imagine this is kind of arbitrary, the way that this plastic thing is held there. Maybe it's held there by a string, like the pith ball, and it's charged to -10 nanocoulombs. So you should hopefully recall, and especially for this course, you're going to use the prefix nano many times. So nano, all right, the prefix nano is just the lowercase n, and that's equivalent to times 10 to the -9th. So 9 nano. Okay, so we're going to use it a lot. Nano, we're going to use a lot. So you're going to, whether you memorize it or not, it's eventually going to be memorized because you're going to use it so much. So that's how much charge this plastic sphere has, and it's held 1 centimeter above a small glass bead at rest on a table. Okay, and all right, so maybe let's just pretend that this plastic bead is hanging there by a string. Okay, just to help us be like, why is it hanging there? Why is it just there? And of course, a glass bead can rest on a table. It's very light. So it's very small too. It's almost like a piece of sand, but they do exist. I have some here in the demonstration lab, and it's sitting on a table. It's at rest. Okay, so we have a picture here with a free body diagram, right? And we see that, gravity obviously pulls down. The normal force of the table on the glass bead pushes up. And if we call the plastic bead charge Q1, right, with -10 nanocoulombs, well, then we could say that charge Q1 is going to exert a force on charge Q2, right? So if we call the glass bead charge Q2, right, we said that the bead has a mass of 15 milligrams and a charge of plus 10 nanocoulombs. Okay, so we could call the plastic sphere charge Q1, which is negative. We could call the glass sphere charge Q2, which is positive, which means are they going to attract or repel? They're going to attract. Okay, and so that means the plastic bead is going to exert a force up toward it, right? So that force is drawn there. And that also will mean that since the glass bead is positively charged, it's going to exert a force toward on the plastic bead. But since the plastic sphere is held there, we're told, right? It's held there. Okay, so it's not going to be able to move. The only thing that's capable of moving potentially is the glass bead. Okay, because it's just sitting there. Okay, so will the glass bead leap up to the plastic sphere? Okay, so how are you going to figure this out? Right, essentially what we're saying here is, all right, we have this free body diagram given to us. We're essentially saying, is the force exerted on the bead by the plastic sphere, is it greater than the force that gravity exerts on the bead? Okay, so we'll have to determine two things here. So we can start off with, and you could go the opposite way if you want. You could calculate the force that the plastic sphere exerts on the bead, and then figure out how much force gravity exerts on it, see which one wins. But we'll just find the force of gravity first. And you recall that the force of gravity is mass times gravity. And then remember, and if we always want to keep unit consistency when we're solving problems, right? We always want to try to keep everything with the same units, usually SI units. That keeps us from making a lot of mistakes. Okay, so anytime we see mass, remember we always want to put that into kilograms, right? So 15 milligrams is going to be 15 times 10 to the millis minus 3. Okay. Oh, and then so that would be how many grams, but then a kilo is 1,000, so we got to go over another 3, so that's minus 6. So be careful of that there. I almost made that mistake of just doing milligrams to grams, but remember that the SI unit for mass is the kilogram. So we always want to keep things with their SI units in order to get proper answers. So gravity, remember, is 9.8 meters per second squared. Okay, and so if we multiply that out, I got so please follow along with me. I know sometimes it's easy to watch a video, and I mean, I've watched videos of people teaching something before, and I'm like, oh yeah, that makes a lot of sense. I get it. And then I try to apply it later, and I'm like, I feel like I didn't learn anything. I thought I was learning something, but yeah. So, and a part of that problem is that I was not participating. I was just kind of watching and saying, oh, it makes sense. So always, the videos are pre-recorded, and that's kind of a benefit, because then you can hit pause and go, what was he talking about? Rewind, try to hear me again, and see if we can try to understand. Sometimes I'll make a mistake. I will make mistakes. Okay, it's impossible for someone not to make a mistake when teaching a whole class. It just happens. And so, so we'll try to, if something doesn't sound right, you can always ask a question. And hopefully between me and Paul, that will hopefully identify any mistakes that I make in the video. And I apologize beforehand if I do that. Yeah, so essentially what I'm saying is pause if you need to get, hear something again, pause so that, you can also be plugging things into your calculator and making sure you're getting the same answer. Okay. And that's going to be really important. That's really what helps make the learning stick in your brain. Okay. Is the actual doing, not just the watching and listening. Okay. I can't reiterate that, how important that is to the learning process in itself. Okay, so please, if you can, please try to do that. It's going to be to your benefit. Okay, so the force of gravity. So when I calculate it, and hopefully you get the same thing, and if not, I would say try it again. And if you're still not getting it, send me an email or go to office hours, and maybe I did do something wrong. Okay, so and if I did do something wrong, I want to tell everybody. I don't want everyone learning something the wrong way. Okay, so that's what I get. So I get newtons. Remember, the force, SI unit for force is newtons. And you said, well, hopefully you remember that. Well, you multiply kilogram by meter per second squared. That's equivalent to a newton. Okay, so that's how we could see that. We definitely have the right units there. Looks like we did everything right anyway. Okay, so that's the force that gravity exerts on the glass bead. What is the force that the plastic bead exerts on, or the plastic sphere exerts on the glass bead? Okay, I'm going to call it Fe. I mean, it doesn't matter what you call it, whatever makes sense to you. If you just want to follow my lead. But, in any situation where, maybe we haven't gone over that exact situation, you can pick whatever subscript you want that makes sense to you. And so we know, but I'm going to put Fe because I know that this is an electric force. Okay. And we learned that an electric force, to determine that, we can use Coulomb's law. Coulomb's law quantifies the electric force between two charges. And so we learned that is K, the electrostatic constant, times the magnitude of each charge. So here we have Q1 and Q2. And it's divided by the distance between them squared. Okay, and so we can start plugging some numbers in here. K is, well, it's 8.99, but remember I said I'm just gonna do 9 times 10 to the 9th just to kind of keep things a little bit simpler and easier to work with when we're getting these estimations. Okay, I know in mastering physics it can be kind of annoying, and if you're a certain amount of significant figures off, it might get a little irritating, and they'll want you to do it exactly. So I would say for mastering physics, yeah, you want to make sure you're using exact just in case that happens, or if you get it wrong, then then maybe think about that. So okay, and then we have Q1 is minus 10 times 10 to the minus 9th coulombs, and Q2 is positive 10 times 10 to the minus 9th coulombs, all divided by distance between them is 1 centimeter. So that's 1 times 10 to the minus 2 meters. Right? Don't forget the square. Okay, it's really easy to make the mistake of forgetting to square. Okay, and so it seems like the bead might not be intuitive here, but the glass bead is so tiny; it's like a piece of sand, and you're dealing with a centimeter distance and a plastic sphere. So probably you don't need to worry about the diameter of them, and we weren't given it anyway, so that's probably another clue that we don't have to worry about it. Okay, so when I calculated, I got 9 times 10 to the minus 3 newtons. Okay, and it's at this point that I sometimes go, what was I even looking for? Because I just did so much work here. Well, the question was, will the glass bead leap up to the plastic sphere? All right, so we found the force exerted by gravity. All right, 1.4 times 10 to the minus 4. We found the force, the electric force exerted upward on the glass bead, 9 times 10 to the minus 3 newtons. Okay, and so will the glass bead leap up? Yes, it will. Okay, all right, because the electric force is greater than the force due to gravity. Okay. All right, 10 to the minus 3 is bigger than 10 to the minus 4. Okay. Okay. So like I said in the introduction, that we're going to be doing a lot of things in this course that we're going to apply from mechanics, the things we learned in mechanics and physics in the previous prerequisite to this course, which was forces. We're dealing with forces a lot, so we can't throw out what we learned in 151. We were dealing with Newton's laws. Okay, force, weight is mass times gravity, equal and opposite forces, Newton's third law. We're going to deal with friction and tension, equilibrium, constant acceleration. So these things aren't going away, and you're starting to see that here now, especially in this problem. Okay, so another thing I'll point out now is that we have, remember I talked about this electrostatic constant K. Okay, it is directly related to another very important constant that we call the permittivity constant, okay, which is epsilon naught. Okay, so the Greek letter epsilon and subscript 0 or naught for 0. So that's the permittivity constant. Okay, 8.85 times 10 to the minus 12. Can also be written in terms of pi as well. So if you see that in the book, you can use it either which way, doesn't matter. But these two constants are directly related. Okay, and this is the relationship. All right, epsilon naught is 1 over 4 pi times k. Okay, so sometimes you'll see it might be convenient to use one form or the other. That's the only reason you'd really want to do that. And so remember that force was K, right, times, the Coulomb's law was the force is K times the magnitude of the charges divided by the distance between them squared. Okay, if we wanted to put it in terms of epsilon naught, it would be 1 over 4 pi epsilon naught times the magnitude of Q1 and Q2 over the distance between them squared. Okay, so it just depends on the scenario, and in the next chapter, next couple chapters, we'll actually see why it's useful to put things in terms of epsilon naught. But I just want to start throwing this term out at you now so that it can start sinking into your brain. Okay, so let's do one last example here with Coulomb's law. And so I have a few charges here. And I want to know what is the force on the minus 10 nanocoulomb charge. Okay, so I have a negative charge over here. I have two positive charges here. and so each of these are going to exert a force pair, right? So there'll be an attraction between these two charges, right, on the right here. They'll attract one another. That'll be one pair of forces. And there'll also be an attraction between the two on the bottom. Okay, and of course the two positives will repel. So what we want to know here is what is the total force, the net force, okay, exerted on the negative 10 nanocoulomb charge. So let's first just so that we can talk about these a little bit more easily, I'm going to assign them a symbol. So I'll call this one Q1, the one where we want to know the force exerted on it. So the minus 10 nanocoulomb charge, I'll call Q1. And let's call the top one Q2. And the plus 10 nanocoulomb, we'll call that Q3. Okay, you can call whichever one you want, but that's what I'll do here. And so what is the net force? Okay, so we recall net force from the previous course, and so here we're going to say what is the net force. I'll say on Q1. Okay, and it's going to be the sum of whatever the force of charge 2 on 1 is, plus the force that charge 3 exerts on 1. Okay, so we just need to know what those two are, add them up together. Okay, but and we'll see it won't be that simple because they're not lying in one dimension, right? They're lying in 2 dimensions here. So it's going to make things a little bit more tricky, but you know how to do that. And I'll go through that with you so you can help recall that. So for first, let's say what is the force that charge 2 exerts on charge 1. Okay, so we know it's K, and it's the magnitude of Q1 and Q2, or the distance between them squared. Okay, that's going to be K is 9 times 10 to the 9th. Charge Q1 is minus 10 times 10 to the minus 9th coulombs. Q2 is 8 times 10 to the minus 9th coulombs over the distance between them squared, that 1 centimeter. So 1 times 10 to the minus 2 meters. And don't forget squared. Okay, so when I did that out, and hopefully you'll get the same thing here, I got 7.2 times 10 to the minus 3 newtons. Okay, and so since we're dealing with 2 dimensions here, what I'm going to do is I want to kind of describe that somehow. What are these 2 dimensions? So we can make a coordinate plane somewhere. So I'm just gonna, you can put it wherever you want that makes sense to you, but I'm gonna call Q3. I'm just gonna put the origin there. Okay. Okay, so let's say we have a y-axis, and then we have an x-axis. Okay, and then we could say Q3 is at the origin. I mean, we could do it however you want. Put the origin, put the origin here on Q1, put it on Q2, whatever you think makes sense to you. So what we can say here is that what's going to happen? We know that we calculated the magnitude that force 2 exerts on 1. Okay, so force 2 is going to exert this upward force, right, on 1. Okay, so toward the positive y direction. And so to represent that, I'm going to use unit vectors like we learned about. Okay, and we know that a unit vector in the positive y direction is j hat. Okay, so I'm going to keep that there, just sort of a way to remind me that I'm dealing with that's the direction it's moving in. Okay. All right, so that's the force of 2 on 1. Now, what about the force of 3 on 1? Okay, again, it's going to be k, 9 times 10 to the 9th, times, this time it'll be q1, magnitude of q1, 10 times 10 to the minus 9th coulombs, and the magnitude of q3, 10 times 10 to the minus 9th coulombs, over the distance between them squared. Now that's 3 centimeters. So that would be 3 times 10 to the minus 2 meters. Don't forget to square, right? And so doing all that out, the force of 3 on 1 is 1 I got, times 10 to the minus 3 newtons. Okay, and so we see that that's attraction again. So charge 3 will cause charge 1 to move in the negative x direction. Okay, and so I could put a minus I hat here just to remind me of what direction that's going in. Okay, and so now I have the two forces. One's going in the positive j hat direction, one's going in the negative I hat direction. Okay, so now we have to find what's the total force. All right, so these are perpendicular to each other. So the total force, right? So if we were to draw, sort of like a little diagram of this, more simplified diagram, we can have, let's say this is a force of 3 on 1, right? It's moving toward the negative x direction. Force of the force of, let's see, 2 on 1 is going the positive y direction. I'll just put, remember we had vectors from head to tail. And so the direction essentially that the minus 10 nanocoulomb charge is going to move, right, is like this. Okay, I'll use this green arrow for, that's the net force. Okay, and this one that points up, force of 2 on 1. Yeah, so essentially we want to know this, right? We know the components, right? One is going to pull it to the left, one is going to pull it up. Okay, so now we form a right triangle. We essentially have the Pythagorean theorem, right? So we can do a squared plus b squared equals c squared. Okay, and we'll call this A, this B, and this C. Okay, and we've calculated this, right? So A squared, f of 3 on 1, that is 1 times 10 to the minus 3 squared. And then B, that's the force of 2 on 1. That's going to be 7.2 times 10 to the minus 3 squared, and that's equal to c squared. So, which is the total force. So when we solve that out, c comes out to be, I got 7.3 times 10 to the minus 3. Okay, newtons. Okay, so the force, so the net force on Q1 is 7.3. times 10 to the minus 3 newtons. Okay, so essentially, right, if we look back up on our original sketch, this is going to be the direction it moves, right? Okay, it's going to move sort of like in that direction. Okay, so we have the magnitude of it, but what about the direction? Right? What direction is it going to move? Okay, well, the way we have it set up here, we can find this angle, right, which is equivalent to this angle here. Okay, so we can find that angle, and that will tell us the direction with respect to the negative x-axis. So that's some information. All right, so let's do that. So we know all three sides. Now we can use any trig function we want. I like to use tangent. So the tangent of the angle is the opposite over adjacent. So the opposite is force of 2 on 1. And the adjacent is force of 3 on 1. Okay. And force of 2 on 1 is at 7.2 times 10 to the minus 3. Force of 3 on 1 is 1 times 10 to the minus 3. All right. And theta, we find the inverse tangent of that, and I get about 82 degrees. Okay, so 82 degrees is this angle. Okay, so that's some information. Typically, we like to measure with respect to the positive x-axis, though, if you recall. So that's easy to find out, though, right? Because if this, right, we coordinate plane on our sketch here. Okay. If we know that this is 82 degrees, then this part has to be 8 degrees, right? So, and then that's a total of 98 degrees with respect to the positive x-axis. Okay, so I'll just put over here. That's with respect to the negative x-axis. But for my final answer, I'm going to choose to say 98 degrees with respect to the positive x-axis. Okay, so some more questions on the homework number 1 that you should now be able to do, and I've done a few we've done, or Aiden or I. Mostly Aiden has done a few extra example problems that might be helpful to you with trying to understand this and complete these homework problems. And so, did you learn to use Coulomb's law to analyze the forces between charged particles? Right. So we said that Coulomb's law was that essentially equal in magnitude but opposite in direction. And we saw that we could determine it in terms of the electrostatic constant K, or in terms of the permittivity constant epsilon naught. And these are the two quantities, those two constants there. Okay, so at the end of the lessons, I try to also collect the relevant equations for all these quantifiable things, and also any kind of constants or things like that are important. Okay, and then second learning objective was to apply Newtonian mechanics to charged particles. So we saw that we were able to apply it like to that glass bead. Okay, we had to look at essentially find determine all the forces acting on the bead, and compare that with the force due to gravity. Okay, and that's it for lesson 2.